Alright, welcome back. In this video, we're going to do some transformations of sine x and cosine x, and so we're going to graph the more complicated examples. And so, in the last video, we kind of developed the graphs of y equals sine x and y equals cosine x, and if you haven't seen those yet, or if you don't know where those graphs come from, you need to go back and watch those, and I'm probably suggesting that, or right up here somewhere, and so you can go back and do that first. It doesn't take that long, okay, and it's worth going through and understanding, okay, because I'm just going to kind of assume these four parent graphs, and then we'll work with them from there. But right now, I need you to think back to last semester when we were talking about transformations of functions. Okay, so recall the impact of a, b, c, and d when graphing y equals a times f of b times x minus c plus d. Okay, so we need to figure out which of these letters is corresponding to which of these transformations. All right, so vertical dilation, that's where we're multiplying the output values, where we're getting taller or less tall, right? And so that's going to be the multiplier on the outside. That's multiplication by a factor of A. That's going to be the vertical dilation factor. Now, a vertical shift, that's movement up and down. So it's going to be a vertical translation of D units, okay? Positive or negative, right? Because we could be adding d, which could be a negative number. That would be fine. And then for a horizontal dilation, that has to do with the multiplier on the inside of the function, on the input, because horizontal values, those are our input values. It's the opposite of the way we expect, though. It's by a factor of 1 over b. And if you need to remind yourself on why that's true, you need to go back and look at Unit 5 when we were talking about transformations of functions. We explained that. We really thought pretty seriously about this. But if that was kind of unclear to you at the time, this is where it's really I think this is really where it's gonna hit home, because the graphs of these waves, the vertical and horizontal aspects of them are very independent. So it's really easy to do the horizontal dilations and see that it's, see what's happening. The wave gets crunched or it gets stretched out like a spring. Okay, and so the horizontal shift, that's the number that's getting added or subtracted on the inside, that's c. Okay, but I'm gonna point out it's positive c units when we're subtracting c on the inside of the function. Again, the opposite of the way we expected. And if you're unsure about that, either just hold on and keep trying to understand as we move forward, or go back to Unit 5 and go review some of those things. All right, so now I'm going to kind of go through each of the aspects of the graph and think about what's going to be, like what in the formula for one of these sinusoidal functions is going to cause the change in the amplitude, the midline, the period, and even the starting point. We'll have new terminology for that. So find the amplitude of f of x equals 2 times the sine of x. Okay, well, the graph of y equals 2 times the sine of x is going to look very similar to the graph of y equals sine of x. It's just going to be vertically dilated by a factor of 2. So I might just borrow that graph from up above. That was a graph of y equals sine of regular sine of x. And if it was 2 times the sine of x, well, it would just reach up 2 times as high and 2 times as far down. So the amplitude, half the distance from the maximum to the minimum, that would be amplitude 2. I'm just going to call that a equals 2. And you saw earlier when we talked about the graph of a times f of x, b, f, whatever, all those A, B, C, and D numbers. I'm going to try to use the same kind of colors and terminology here. Okay, so the amplitude was 2 sine x. Find the amplitude of g of x equals 1/3 of the cosine of x plus 1. Okay, now I haven't really talked about the impact on the midline, but that plus 1 is going to be a vertical shift, which is going to move the whole thing up 1 unit, which is going to bring the midline with it. So that plus 1 is going to impact the midline, but it's not going to affect the height of the wave. That's what I'm saying. So the amplitude of this one is going to be 1/3. And that's what I'm saying. We're discovering that the actual thing that's causing the amplitude to change is the vertical dilation factor. Now, without getting too deep into the window pane graphing technique, if we wanted to graph this thing, we could start with a standard cosine, and we could say, oh, hey, I moved up by 1, and then the amplitude's 1/3, so it'd be 1 plus 1/3 and 1 minus 1/3. But I'll get into that more in a few seconds here. All right, now talking about midline, okay, what's going to impact the midline is going to be a vertical shift, like I was just saying earlier. And it might have made more sense for me to talk about midline before amplitude, but I put it first in the notes, so I'm just going to do it first here. I think if we were asked about the midline of f of x as sine of 2x plus 3, we might go ahead and make a window, draw our standard y equals sine x graph. say, hey, this thing got shifted up 3 units, so instead of being like 0 in the middle, that's going to be a 3 there, and then the amplitude, the number that's multiplied out the front, is still 1, so it'll go up to 4 and down to 2. Now, horizontally speaking, I don't think it really matters, right? Because what matters is thinking about the midline. Where did it move? The midline is a horizontal line. It would have gotten shifted up and down. It got shifted up by 3 units, meaning that the midline there is y equals 3. Now, for the graph of g of x equals 4 times the cosine of x minus pi over 5, I've subtracted pi over 5 on the inside, and that's going to be a horizontal translation. And this one has no vertical translation, so I know that the midline hasn't shifted at all. So it has the same midline as the graph of y equals cosine of regular x, and so that's going to have midline y equals 0. Really, because I'm adding that 0 on the outside. Right, now I'm going to tell you about something new, okay, because we didn't really need to worry about this all that much with the graph of y equals sine x and cosine x, because we just wanted to start with x equals 0, because we just wanted to start with kind of the most basic graph. But if we have a horizontal translation, we're going to call that a phase shift. And so in this class, a phase shift is just going to mean a horizontal translation of a sinusoidal function. Okay, so what is the phase shift for f of x equals 2 times the sine of 3 times x minus 4? We'll go back to the definition. Phase shift by negative c units, so that would be negative of negative 4 is phase shift 4 units. And then over here, this is something different. And I think I'm going to even switch up my color of pen just to remind you about it. Pretty sure I've told you somewhere along the line that this isn't going to happen in AP Pre-Cal, because if you start getting into like factored and unfactored, then the order of the transformations matters, and it seems like based on what we've seen in AP Classroom, they always give it to you factored. But in the wider world of mathematics, you might not always encounter a function that's like factored up real nicely like this. You could have something like 2x plus pi. So what I would, emphasize is that, we could rewrite g of x by factoring out the 2. So that's cosine of 2 times x plus pi over 2. And that would mean that the phase shift of this thing would be negative pi over 2. But also, I'm telling you that I don't believe that you would ever need to do this in AP Pre-Calculus. This doesn't seem like a necessary thing. So you can think of this as a typing error, but in reality it was not. I just wanted to remind you that that wasn't something you had to worry about. But it's the number that's been subtracted on the inside after the factoring, right? So we need to be looking at it in a form that looks a whole lot like what you're seeing with f of x. This 3 times x minus 4. Then we're just reading the phase shift right out of there. But that's how it will always be in this class. Alright, now the last thing is I need to remind you about period, which is something we talked about in the last video. So remember that the period for the standard sine and cosine graphs is going to be 2 pi. And so a horizontal dilation of the graph of a sinusoidal function will cause a change to the period. And so I just want to kind of like develop the idea here, and then I'm going to give you a formula that we're going to work with extensively in this unit to determine period and like the values that go inside of the function when we're modeling. All right, so first, find the period of the sinusoidal function. Well, I would emphasize over here that, I don't want a blue highlighter, I want a blue pen. So that 4 there means I'm going to horizontally dilate by a factor of 1/4. And then as a result, we can say the same thing's going to happen to the period. So the period is going to be 2 pi multiplied by the horizontal dilation factor, which is going to be that 1/4. And then we could go ahead and simplify that. 2 pi divided by 4, that's going to be pi over 2. Okay, so that's going to be the period of the sinusoidal function. And then for g of x, we're going to notice that x minus 1, which does mean there's going to be a phase shift of 1, but not going to be relevant to our period discussion here, it's been multiplied by pi. So that means we've got a horizontal dilation by a factor of 1 over pi. So if I do kind of the same type of computation, the period is going to equal 2 pi times the dilation factor, which was 1 over pi. And if I were to simplify that, I'd get period of 2. All right, so before we go on too many more examples like this, I think we want to kind of like condense this process, because really what we did was we took 2 pi and we divided it by that number, that multiplier. So what we're going to say is for y equals the sine of b times x minus c and y equals the cosine of b times x minus c, and any sort of vertical transformations of those, the period is going to equal, hold on, there it is, 2 pi divided by b. Okay, because we're multiplying 2 pi by the horizontal dilation factor, which is necessarily 1 over b. And this is going to be a formula we need to just know and apply very regularly in this unit. Period equals 2 pi over b for sine x and cosine x. All right, so for example, here I'm going to give you the period of the sinusoidal function, find the value of k, so that's basically b. So period equals 2 pi divided by k in this case. I'm going to write that formula out so that we can just kind of because k is the multiplier on x, and that'll be an important formula for us. All right, so over here, period is half, so period equals 2 pi divided by k. Okay, and I like, mostly on these, I think you should use cross multiplication. I've worked a few of these and made a few errors, and so I think for me, and the rest of the way through, I'm going to try to just use cross multiplication. Try to limit those errors as much as possible. K times 1 is 2 times 2 pi. K is equal to 4 pi. Okay, that's going to be a good answer for us. And then if the period is 5 pi, I'll say 5 pi equals 2 pi over b, or in this case 2 pi over k. If I want to do cross multiplication, probably write it as over 1, multiply 5 pi times k is going to equal 2 pi times 1. So I can divide both sides by 5 pi. I can cancel out the pi's, and I'll get that k is going to equal 2/5. So that's how a problem like that would go. And now let's move forward and start graphing some of these transforms. All right, so I've already been doing it already in these videos, but we're really going to focus in on the window pane graphing technique here. And I'm going to kind of give you like a procedure and maybe an order to go in that will kind of help you make the best graph possible and kind of like not forget any of the things you're supposed to remember about the aspects of these graphs. Me personally, I like to start with the vertical things, but not okay. The very first thing we need to do is think about what type of graph do we have. And I'm seeing f of x as sine of 2x. I can just stop at the sign. This is a positive sign, so I'm going to fill that in. Remember, sine, or at least regular sine, starts in the middle going up. Starts in the at the midline increasing. Okay, and then we'll just fill out one cycle of sine that way. And then we're going to go in and graph it as nice as we can without obsessing. It doesn't have to be perfect. We're going to go up like that. Okay, that's the graph of y equals regular sine x. And then we're going to label the axes, the vertical and horizontal like aspects of this according to the transformations, and then draw the x and y axes last of all. If you think about it, when you're graphing something normally, you usually start with the x and y axes and then work from there. But I find that with sinusoidal functions, you really want to do the x and y axes last because they can kind of like cause you to make your graph look bad. Okay, so the first thing I would recommend is midline. Remember, the midline is affected by a vertical translation, so it's that number that's added onto the outside. So I'm going to say midline is going to be y equals 1, and so I'm going to label that right there. That's my midline. Okay, then I might think about the amplitude, because the midline and the amplitude go together because they're affecting the verticality. Okay, so the amplitude is the number that's multiplied out in front of the sign, and I don't see anything there, so that must mean the amplitude is 1. Okay, so I'm going to go up by 1 and down by 1. Okay? And then I need to think about the phase shift. Okay, where am I starting horizontally? Okay, I don't see x added to anything or subtracted to anything on the inside of sine, so the phase shift is going to be 0. Okay, so that means that on x, I'm starting there at 0. And then the last thing I would figure out, unless I'd already figured it out earlier, is going to be the period. Okay, so that's going to be related to that too. So remember, period, I'm going to find that off to the side. Period equals 2 pi divided by b, which was 2. Okay, so 2 pi over 2 is 1 pi. Now, 1 period is how long it takes to graph one full cycle. And that's what we've done here on our picture. We've graphed one full cycle, so that means I've gone to the right pi units. And then from there, I'm going to recommend that you just fill in the other 3 points, just like however you're going to do it. Do the best you can. Okay, one thing that will always work is you can just average to get in the middle, and then average the things to get the middles from there. Okay, so halfway between 0 and pi is pi over 2. Halfway between 0 and pi over 2 is pi over 4. And that would make this 3 pi over 4. But however you want to do it, it works for me. I just want you to have the accurate numbers there. Last of all, we're going to graph the x and y axes. Now the y-axis, that's going to be where x equals 0. So I'm going to just kind of draw in a vertical axis there. And it's not perfect, but that'll work for me. And then a horizontal axis, the x-axis, that'll be right there where y is equal to 0. Okay, that looks pretty good. And I'll label that, and there we've got ourselves a really nice graph of f of x equals sine of 2x plus 1. It's just one cycle, but we have a good perspective, we have the idea of what it's doing, and we can envision it doing the rest of its cycles, right? We don't need to graph all of the cycles. All right, for the next one, I'm going to go a little bit faster, and I'm going to emphasize that I'm going in the same order here. But I am going to change this example to be a little bit better because we've only got 4 on this page. I'm only going to do 4 in this video. I'm going to do a bunch in the homework video and the examples video. But I'm going to add 1 to this so it's got a little more excitement going on. All right, so first things first, I'm going to think about what kind of graph do I have here. I have a positive cosine graph, so I'm going to get my standard positive cosine, which starts at the top at its maximum. Then I'm going to think about the midline. I added that 1 to the question, so that's going to make the midline 1 because I'm seeing that addition on the outside. So I'm going to write midline y equals 1. Okay, then I'm going to think about the amplitude, and the amplitude is going to be from the vertical dilation factor, which is the number that's multiplied by the sine or the cosine. That's going to be 3. So I'm going to say that the amplitude's 3, and that means that the graph is going to reach all the way up to 1 plus 3, which is 4, and down to 1 minus 3, which is negative 2. Okay, after that, I'm going to think about the phase shift, and the phase shift is what I'm subtracting on the inside of the sine or cosine. What's next to the x, since that's x minus pi over 2, that means the phase shift will be pi over 2. And so I'll label that spot where my graph is beginning right there. That'll be a pi over 2. Okay, now the last thing I need is the period. The period I'll get from using the formula period equals 2 pi over b. And right, if this is your job to know the formula and you don't know it yet, you need to just write it down and say it out loud a bunch of times. That's what I'm doing for you. I'm writing it down in my own handwriting. I'm saying it out loud so I can remember it. And actually, I think I'm going to remember it a little too well because I was having trouble when I was working the third homework because it was a slightly different formula from when we were graphing tangent. Okay, but anyway, b is looking like it's going to be 1 because nothing's multiplying by the x, so period's going to be 2 pi. And then from there, I know that I need to go to the right by 2 pi to complete one full cycle of the graph. So pi over 2 plus 2 pi, so I'm just going to put it in terms of pi's over 2, that's 4 pi over 2. So I'm going to add 4 pi over 2 to pi over 2, that'll be 5 pi over 2. And, well, if you think about it, if I've got 4 squares and the period is 4 pi over 2, each of those squares is going to be 1 pi over 2. And so that'll be kind of useful. 2 pi over 2, 3 pi over 2, 4 pi over 2, and 5 pi over 2. And here I've made myself, like a really good graph. Okay, the only thing I have left now is to do the x and y axes. Now the x-axis will be about like that, and it would, favor the 1 a little more than the negative 2, just because of 1 being closer to 0 than negative 2. I don't know if that was quite right to scale, but that's all right. Pi over 2, I don't know, it's about 1.5, but, as far as, its distance from pi versus its distance from 0, let's not worry about that too much. Let's say it's a positive number, so the y-axis is going to go over there to the left of it, and there we have ourselves a really nice sketch. All right, for this next one, I'm seeing 5 minus 2 sine of pi x. I'm seeing a negative sine x, and negative sine starts in the middle but goes down. So I'm going to graph the general form of the negative sine graph, and then I'm going to start labeling stuff based on the aspects of the graph. I'm going to start with the midline. I'm seeing that number 5 added on the outside, so that's going to give me my midline. Midline y equals 5, label that on the graph. Okay, next I'm going to think about amplitude. That's the number that's multiplied by the sine or the cosine, so that's going to be the 2. I already dealt with the fact that it was negative by doing that upside down sine graph. So I'm going to say, all right, the 2 is giving me amplitude 2, so it means the graph will go up to 7 and down to 3. Okay. Then I'm going to think about the phase shift. I don't see x added or subtracted to anything on the inside of the sine, so the phase shift is going to be 0, and that'll be where my window is starting. Okay. Now I have to think about the period. The period is going to be 2 pi over b. Okay. B is the number that's multiplied by the x, and that's going to be the pi. So I'm going to say, all right, that means period's going to be 2 pi divided by pi. I can cancel those off, and notice that means that period's going to equal 2. So the right edge of my window is going to be at x equals 2, meaning halfway in the middle is x equals 1. I can just fill in the other 2 from there, right? There's no shame in using decimals here. Now the last step of all would be adding in x and y axes, and I'll be honest, that's not the most important step. That's not something you're going to be graded on in this class. It's just something I like to do to make the graph look extra nice, okay? And, it might not be drawn quite to scale, but there we go. We're seeing it's in our first cycle of the graphs in the first quadrant, and that's going to be plenty for us. All right, even faster for this last one. First, notice it's a negative cosine. Graph that. Then go to the midline. Midline's going to be -2. So I'm going to label that on my graph. Then I'm going to think about amplitude. Amplitude is the number that's multiplied on the outside. I'm only seeing the negative, so that means the amplitude is 1. Okay, so that means I'm going to go up to -1 and down to -3. Then I'm going to think about the phase shift. X isn't added or subtracted to anything, so the phase shift is going to be 0, and that'll be where my window starts. Now I think about the period, right? Remember, period equals 2 pi over b. Find b. That's going to be 2/3. Okay, so report that, plug that into your formula, keep, change, flip, or do, however you're going to do the fraction arithmetic, figure it out. It's going to be 3 pi. Okay, that means the right edge of my window is going to be 0 plus 3 pi, which is 3 pi. And then I'm just going to figure out the rest of them from there. That means in the middle would be 1.5 pi, or 3 pi over 2. To me, that means the first one between 0 and 3 pi over 2 would be 3 pi over 4. Okay, and then the last one, that's going to be 9 pi over 4, and let you figure that out however you're going to do it. 3 pi over 4, 6 pi over 4, 9 pi over 4, 12 pi over 4. I'd say in this class it's alright if you don't simplify these values down there, probably because we're not going to really be making a graph isn't really part of the course. Okay, so that's going to be all the examples for this video. Actually, there was one more step I forgot to put in, my axes, right? Okay, but that's by far the least important step. That's going to be all the examples for this one. At this point, you need to just go forth and do some of these on your own. And we do have some that are a little more complex than these on the homework, but ones like these are going to be the most essential. So that's going to be all for this video. Thanks for watching.